Hello, this is Team Two's presentation. For our design project, we selected Colgan Air Flight 3407. It's commonly called the Buffalo Crash. This was really a watershed event in commercial aviation in this country, fairly recent, that resulted in a lot of changes, not only to company operating procedures, but also FAA hiring procedures and minimum requirements for pilots. Um, a little background on the flight. It occurred in February of 2009. It was a scheduled regional jet flight from Newark, New Jersey to Buffalo, New York. They were flying a Bombardier Dash 8, which is kind of the standard turboprop aircraft for short haul regional airlines in the US, especially at that time. Twin engine turboprop, 360 knot cruise speed, typical operating altitudes in the mid 20s. And it ended up crashing on approach 5 miles from the end of the runway, killing all people aboard the aircraft, as well as some people on the ground. The flight deck crew was a fairly junior captain. He was 47 years old, but had worked his whole life in an industry other than the aviation industry, so he's fairly new. You can see he only had about 3,300 flight hours and about 100 hours as a captain in the Dash 8. He had a history of failed FAA check rides as well as failing company training events. And we know from the black box recording that he was the one physically at the controls at the time the aircraft crashed. His first officer was a young female who had recently graduated from Arizona State's aviation program. She had very few hours in turbine type aircraft. Almost all of her time was in small, light civil aircraft, where some of the training doesn't quite translate over, as we'll talk to you in a minute. Also, factors in the flight, because it was Buffalo in February, as you might imagine, there was some light snow, fog, icing conditions, and wind was blowing about 15 knots. So not the easiest of flight conditions. Some other pertinent background information for the condition of the aircraft at the time of this incident was the autopilot was engaged. That's not recommended in icing conditions by either Colgan's company policy or the NTSB. The stick shaker was a kind of a stall warning and stall protective device that was installed in the aircraft, and it did activate. So the automation in the aircraft was recognizing that they were coming into icing conditions, but the crew didn't recognize it. And because they didn't recognize it, the captain pulled back on the controls, applying 160 pounds of aft stick force, so he was really yanking on it. And he increased power to only 75%, which were completely the wrong recovery procedures, where you'd want to kind of push the nose forward and increase to 100% power. While the captain was doing that and the aircraft was in the process of entering a stall, the first officer, without informing the captain, just hit the flap handle up. This was probably negative transfer from prior aircraft. In light civils, you want to get the flaps up at least out of the landing detent to cut down on drag, but in turboprop aircraft, that's not the correct procedure. Well, the captain, through all this, continued to just reef back on the controls, never relaxed his pressure or applied any forward stick, which brought the aircraft to a full stall and ultimately a loss of control, and they crashed. They crashed into a house about 5 miles from the approach end of the runway with 51 fatalities.
All right, so starting into our risk process here, we started off with a risk management plan. Kind of went through the typical standard process of identifying, analyzing, handling, and then monitoring and controlling the risks. Those risks that would have been identified went through the risk cube, as you can see on the top right of the slide, and then were registered into the appropriate risk register for the risk management process. So from there, we generated two fault trees for two top-level failure events, as you see there, for stall warning and aircraft stall. Each FTA was then converted to a reliability block diagram, and probabilities of occurrence for those two top-level failure events were calculated based off of a couple of probabilities that you can see at the bottom of the slide.
So this is an example of one of the fault trees that we created for the aircraft stall case. You can see there's lots of blocks and a bunch of potential initiating events there. Since it was outside the scope of this investigation to look at all of them, we picked two, namely the one circled in red there, the stall warning, and the air data sensing system failure. And we further created fault trees and event trees for those, and looked at use that to address the probabilities.
All right, so the first FTA stall warning, see the FTA on the bottom left, the RBD on the bottom right. So we calculated a probability of the stall warning occurring as you can see the 2 to the negative times 10 to the negative 3 per flight hour, with a minimal number of minimal cut sets as 10. Going through the FTA, a couple of the recommendations we kind of noted to improve that probability potentially in the future would be to improve the pilot training with respect to icing conditions, how to handle those icing conditions when they are encountered, as well as how to use and general knowledge of ice detection systems, as well as incorporating an aircraft ice detection system.
So with the second initiating event we looked at was an air data sensing system failure. You can see that the probability of failure is much lower per flight hour. It's another whole order of magnitude lower than the stall warning system failure. There are also fewer cut sets at 9 versus 10 with the other one. You can see the tree there to the left, and then you can see on the RBD on the right, there's a lot of redundancy built with those AND gates and the parallel blocks there. So it's a system that is fairly critical to flight, as anyone who's flown knows. So there was a lot of redundancy built into it, which kind of explains the lower probability. Still, if you kind of look through the tree there, you can see that that there are some places where you could improve it, and with basically adding one more block in a strategic place on that fault tree, you can drastically reduce that probability of failure. So two of our recommended improvements with what looks like good bang for the buck is you could put additional redundancy in the physical components. There's a lot of failures resulting to either just physical damage or icing of a couple of components on there. So if you add more redundancy there, as a lot of larger airliners do, you get a lot of benefit there. The other one would be adding a redundant air data computer. This aircraft didn't have it. It really just had one central processor running through a couple of different systems of physical tubes on the outside of the aircraft, but really only one processor. And if you look on the far right of the fault tree, you can see there's only a couple of little diamonds there going into an AND gate. So that's a place that would be easy to kind of double it up for a low weight, a fairly low cost, with a significant benefit to the safety.
All right, after the fault tree analysis, we moved into the event tree analysis. Again, we conducted two, one for stall warning and one for air data sensing system failure. Just like the FTAs, we used assumed some probabilities of failures to calculate the end state probabilities. From there, we then combined kind of the common end states, grouped them together for further analysis, and then we calculated the mean time between occurrences for each type of end state.
This is one of the sample ETAs we had. As you might have been able to guess from the earlier fault tree we showed, there were lots of gates, fairly complex, lots of barriers, which is good for a commercial airliner. It makes the analysis a little tedious for us. So this one is specifically the aircraft stalled case, running with the air data system failure as the initiating event on the left there. I think it had 67 outcomes, and we kind of racked and stacked them with severity, kind of red, yellow, green for goodness and badness. So just a sample to show you kind of how the analysis went.
All right, so our probabilities based on our two ETAs. As you kind of see, the red is bad. So both scenarios, or both ETAs, loss of aircraft was ultimately the most negative consequence that we came up with. Both of which, fortunately for both ETAs, had the lowest probability of occurrence, which is kind of what you want to see is the highest consequence have the lowest probability. And with each case also having the best consequence with the highest probability. As you can see with aircraft continues flying with stall warning, and then air data sensing system failure, aircraft continues flying or just lands firmly, which isn't necessarily desired, but better than crashing. As well, you can also see the mean time between occurrences for each scenario. Also kind of follows along with the probability as well. All right, moving on from there into the PRA, and kind of talked about our mean time between occurrences here a little bit more. For the stall warning, you can see just how big of a difference between crashing and even just recovering from the stall was. And then as well, same thing with the air data system failure, just the big difference between the crash and chances of even getting into a stall and recovering. On the right, we kind of picked out what the paths were the most dominant and least dominant. It kind of shows like what things you could change or focus on to improve the probabilities moving forward. For the stall warning, by far the most dominant path led to aircraft continues flying, with a lot of the loss of aircraft paths being in the same order of magnitude of the 10 to the negative 14 there. And then we saw something similar with the air data system failures. Kind of what you want to see is that the good stuff, higher probability, the bad stuff, a lot lower probability.
So from this risk assessment, we were able to summarize and get some lessons learned from it and some recommendations for how to actually improve the system to reduce the likelihood of this incident happening in the future. One of the ones we saw was that more resources should be dedicated to improving the stall warning case, additional redundancy in the stall warning system, an automated ice detection system, and additional pilot training and stall recognition and recovery were kind of the three that we saw that would have the biggest effect on positively influencing that. There's a high level of redundancy already in the air data system, which greatly increased its robustness and failure resistance, which is why you kind of saw the order of magnitude differences in the mean time between failure, mean time between crashes, based on those two initiating events between the stall warning case and the air data system case. What was interesting as we looked at kind of the greater system and the greater fault tree was those three recommendations above, namely the redundant stall warning system, automating the ice detection system, and adding additional pilot training for stall recognition and recovery. They make the most sense for the air data system failure case as well. So that would be our recommendation there, kind of common to both initiating events, which is interesting. It'd be kind of fun to look at some more initiating event cases and see if that kind of trend holds through. So overall, from this whole analysis that we've done throughout the semester, we pulled out a couple of kind of key chestnuts just more globally. So we definitely made a lot of assumptions in terms of the system design and specific kind of redundancy and components and that sort of thing, because it is such a complex system. We also had to make some simplifications and assume the probabilities for our barriers and failure events. However, I pulled some statistics off the NTSB website. And if you look at the 2009 statistics, there's about 1 in 75 million flight hour fatality rate due to a mechanical failure on an aircraft, which is order of magnitude with our 99 million that we just showed on the last slide. Also, it looked like 1 in 45 million flight hours was about the commercial aircraft stall rate in 2009, and our number was right there around 50 million. So it's kind of interesting that with all the assumptions and simplifications that we could come up that close to what the actual numbers at the time of this incident were. Also interesting is there's a 200-page NTSB report, which the source is listed on the bottom there. You can Google it and download it for yourself and read it if you want. But even our limited scope investigation, where we really looked at two kind of failure cases, pretty much mirrored the findings that the NTSB came up with, namely that there was insufficient pilot training and inadequate ice detection on the aircraft. And both of those things resulted in new laws and policies being implemented industry-wide. One of the changes that came from that was there was an FAA rule change that said there was a 1,500-hour minimum for first officer qualification. So we kind of agreed with them that that's potentially justifiable. One thing that was outside of scope is we never looked at the overall economic costs to the industry for it. We kind of made almost an intuitive assessment of where adding another block or adding another diamond or parallel branch in a diagram would improve the probability, and played with some sample numbers. We didn't look at the more global picture, which was the economic costs of implementing each one of those things and the effect on the industry. That's probably the most controversial finding from the NTSB report, and thing that's come out of this incident among the industry that still kind of leaves a sour taste in people's mouths. So for follow-on research, that'd be an interesting thing to look at in terms of the economics and the bang for buck. So that concludes our presentation of the Colgan Air Crash. Thanks for listening.